relativistic Lagrangian for a charged particle. The previous class, we have obtained the free particle Lagrangian is mc squared, m0c squared over gamma, and we put the negative sign in order to reproduce the Hamiltonian for the free particle. And explicit expression is minus m0 c squared square root 1 minus 3 squared over c squared. Again, in this case, we make use of the Lorentz invariance of the gamma times Lagrangian. This gamma times Lagrangian must be Lorentz scalar for free particle case, and even for the case for the electromagnetic interaction of the charged particle with mass m and charge q. And let us call that part, the additional part that comes from the electromagnetic interaction is the L interaction, so L int. Again, gamma L int must be a Lorentz scalar. But Lagrangian is T minus U, so kinetic energy is subtracted by potential energy. And potential energy due to the electromagnetic interaction can be computed. So gamma L int can be evaluated in the rest frame of the charged particle. For the charged particle, it acquires two kinds of potential. Electrostatic potential is phi, and the magnetic field is generated from the vector potential A. And in the previous section, from problem 18.1 to 18.5, we have obtained that field strength tensor F mu nu is expressed as round mu A nu minus round mu A mu. Here, A is a 4 vector, and the 4 vector composed of A0 and A vector, and A0 is a phi, that is the electrostatic potential, and A is the vector potential. And that 4 vector potential generates the electric field and magnetic field in such a way. Alright, so we'd like to make use of these potentials to express the electrostatic potential energy in the rest frame of the particle. In the rest frame of the particle, because the particle is not moving, there is no magnetic field. Even though there is a magnetic field, it does not feel any magnetic force. Only it feels the electric field. So Lorentz force is simplified into just the Q times electric field. In that case, the potential energy of the particle is just the charge Q times electrostatic potential phi. Because Lagrangian in the rest frame should be expressed in such a way, negative sign came from the fact that L is T minus U, so minus interaction potential. So in the rest frame of the particle, gamma L int, that is the Lorentz scalar, in the rest frame of particle we write minus Q phi. And this value must be the same in everywhere, right? So why don't we express this Q phi in terms of Lorentz scalar? We know the vector potential, 4 vector potential A is a 4 vector, and we have to find something to make it expressed as a scalar product of two 4 vectors. So we have A mu available, and phi is the zeroth component of A mu. And is there any constant 4 vector that has only zeroth component and the spatial component is vanishing? That is actually the 4 velocity. 4 velocity is gamma c, comma gamma v, something like that. But in the rest frame of particle, it becomes a c, comma 0. So why don't we make use of that fact? So zeroth component of 4 vector A mu is a phi, and phi can be expressed as 1 over c times the c phi, and c is the zeroth component of 4 velocity of the charged particle. So 1 over c times u mu of the charged particle and the 4 vector scalar product. So we have expressed this phi as a scalar product of the four vectors. So, this expression can be used in any frame of reference. That's good. So, gamma L int has been identified to be minus q phi, and then the Lorentz scalar form is q over c, 1 over c, u dot a. So if I divide this gamma in both sides, our final expression for the Lagrangian is free particle case minus mc squared over gamma, and then we have minus q over c u dot a divided by gamma. But this forward velocity is actually expressed in terms of normal velocity, right? So I factor this gamma out, that gamma cancels the gamma in the denominator, and the numerator in the numerator u is gamma c comma v, something like that. So if I substitute that c in the zeros component cancel the denominator, so I have minus q phi as the zeros component, and the spatial component is minus v over c dot a. So we have found that this is the Lagrangian for the charged particle. Relativistic motion is included. Why don't we compute the conjugate momentum that is just partial derivative of the Lagrangian with respect to the I component of the velocity. We know this is obtained from the first kinematic part, and then there is a velocity dependence in the potential energy, right? So velocity dependence in the potential energy gives, if I take this derivative, I have plus minus plus q over c a. This was the momentum, relativistic momentum for the free particle. Okay, so if I include the charged particle interaction, electromagnetic interaction, the replacement of this conjugate momentum is from this free particle momentum by conjugate momentum subtracted by q over c vector potential. Because P is a 4 vector, spatial component of 4 vector, I'd like to see what happens to the zeros component. Zeros component is related to the Hamiltonian, and this is homework. If you compute the Hamiltonian of the system by making use of its Lagrangian and conjugate momentum, the final result is that the Hamiltonian is a sum of electrostatic potential energy plus. This is the expression for the Hamiltonian for the free particle case, but we have made use of this replacement group. If I substitute that momentum part by the P minus Q over CA, then this is the Hamiltonian of the system. Alright, why don't we move this one to the left hand side? Then what we find is 4 vector P mu is a zeros component is Hamiltonian divided by speed of light, and spatial component is normal momentum. That is, that for the free particle is replaced by Hamiltonian subtracted by q phi divided by speed of light, and spatial component is the conjugate momentum subtracted by q over c vector potential. If I combine these two into 4 vector form, then replacement from the free particle case to the charged particle is P mu is replaced by conjugate momentum P mu subtracted by q over c a mu. That's it.